Welcome to Jeremy's IT Lab. This is a complete course for the CCNP ENCOR Enterprise Core exam. In this video, we'll look at some more advanced MSTP-related topics. Specifically, we'll cover MSTP regions and various concepts related to connecting regions together. Here's what we'll cover in this video. First, I'll introduce MST regions. A region is a group of switches that share the same MSTP configurations, as determined by their MCID, MST Configuration Identifier. Once we cover the basics of MST regions, we'll cover various concepts related to connecting MST regions to each other. We'll cover the IST, internal spanning tree, which is MST instance 0, as I mentioned in the previous lecture. We'll also cover the CST, common spanning tree, and CIST, common and internal spanning tree. These concepts are often confused, but I'll do my best to explain them clearly. Before we get started, here is a quick summary of the key concepts. Switches that share the same MSTP configurations, meaning they have the same MCID, are in the same MST region. Switches in an MST region appear as a single logical switch to the outside world. This means that switches in other MST regions see the region as a single switch. The IST is a special MST instance that runs in each MST region. It is the only instance that sends and receives BPDUs, and each MST region has its own IST. If the LAN consists of multiple MST regions, and maybe some switches that don't run MSTP, the CST, common spanning tree, is the spanning tree of connections between MST regions, as well as non-MSTP switches. And the final concept is the CIST, which is a combination of the ISTs from all MST regions and the CST. The CIST ensures a loop-free topology for the entire network by coordinating the spanning tree information within and between MST regions. If this is your first time hearing this, you're probably a bit confused right now, but let's get started and walk through these concepts step by step. First, let's look at MST regions. An MST region is a group of switches that share certain MSTP configurations. These configurations are called the MCID, MST Configuration Identifier. So, what is contained in the MCID? Well, it consists of 4 parts. First is the Configuration Identifier Format Selector. This is a 1-byte value that is always set to 0, and since it's a fixed field, you can ignore it. As far as I know, other uses for this field aren't defined, but they are available for future use. So let's focus on the remaining 3 parts. Next is the configuration name, the name of the region, which you can optionally assign. Third is the configuration revision, which is a 2-byte number that can be incremented as the MSTP configuration is updated. Like the name, configuring a revision level is optional. It doesn't increment automatically when you modify the MSTP configuration, but you can optionally configure it. Finally, and perhaps most importantly, is the configuration digest. This is a hash calculated from the switch's VLAN to MSTI mapping table. I briefly mentioned this in the previous lab video. Instead of directly comparing their tables, each switch calculates a hash from its table and uses that to verify whether it has the same mappings as other switches or not. Let's see how this works. These 2 switches both have the configuration name Region1 and revision number 1. To compare their VLAN to MSTI mappings, they calculate a hash from their mapping tables. That is the configuration digest. In this case, all fields of these switches' MCIDs match, and that means they are in the same region. This is significant because MSTP switches interact differently, depending on if they are in the same region or different regions. We'll see some of those behaviors in this video. Here's an MST BPDU, the same one we looked at briefly in the previous lab video. Can you spot the MCID? Here it is, the config ID format selector, config name, config revision, and config digest. And here's some CLI output showing the same info. The name is blank in this case. As I said, configuring a name is optional. If the name is blank, that blank name is still part of the MCID. And here's the revision number, which is 0 by default. You don't have to configure this, but if you do, you must configure the same number on all switches in the region. and the config digest was calculated from this table of VLAN to instance mappings. Again, this digest must match among all switches in the region. We've seen how to map VLANs to MST instances in the previous video, but let's see how to configure the name and revision number. Before we do that, keep in mind that switch 1, switch 2, and switch 3, as we configured them in the previous video, are already in an MST region. They all have the same MCID, a blank configuration name, the default revision number of 0, and the same VLAN to MSTI mappings. If we modify the name and revision number on one of these switches, we have to modify it on all of them, or else they will no longer be in the same region. To configure the configuration name, the command is simply name followed by the name. I named it Region123. And to configure the revision number, the command is revision followed by the number. Personally, I usually don't configure a revision number. Although it's convenient to configure the configuration name to make it clear which switches in a LAN are part of which MST region, the revision number is kind of useless, to be honest. It's just a number that you can configure, and it has to match among all switches in the region. I usually leave it at 0, but you should know the command to change it. Okay, then I configure the mappings. These are the same mappings I configured in the previous video. I'm just showing them here for review. After, I used end to exit MST config mode. I mentioned this in the previous lab video, but configurations made in MST config mode don't take effect until you exit MST config mode. Finally, I used show spanning tree MST configuration on switch 3, and you can see the name, Region123, and the revision number 1 that we just configured, as well as the VLAN to instance mappings. Ideally, all switches in the LAN will be in the same MST region, keeping things simple. However, in some cases, a multi-region design will be needed. So let's see how that works by adding another region, consisting of switches 4, 5, and 6. We won't connect these regions yet. Let's first examine them independently. Here are the priority values of each switch. Pay attention to the IST in particular, MSTI 0. Switch 1 and switch 5 are both the root bridge of their region's ISTs. Switch 1 has a priority of 4096, and switch 5 has a priority of 0. Here are the port roles for the IST in the region on the left, and the port roles for the region on the right. Showing the port roles for both the IST and each other MST instance would get really messy, so let's just focus on the IST for now. Okay, let's view the configuration of each region. The regions on the left and right are named Region123 and Region456, respectively. They both have a revision number of 1, and let's compare their VLAN mappings. Both map VLANs 1 to 50 to MST instance 1. So VLANs 1 to 50 stretch across the entire LAN, including both regions. Region123 maps VLANs 51 to 100 to instance 2, whereas Region456 maps VLANs 101 to 150 to instance 2. So VLANs 51 to 100 are only used in Region123, and VLANs 101 to 150 are only used in Region456. This is an instance where you might use a multi-region design like this, when certain VLANs are only active in certain parts of the LAN. Finally, in both regions, the remaining unused VLANs are mapped to instance 0, the IST. Now here comes the interesting part. Let's connect these two regions together and see how MSTP converges. When MST regions are connected, each region appears as one logical switch to the outside world. Region123 sees Region456 as one switch, and Region456 sees Region123 as one switch. The spanning tree that connects the regions is called the Common Spanning Tree, CST. Region456 is the root bridge of the CST. We'll see why a couple of slides later. And therefore, these are the port roles of these ports that connect the two regions. Region456, being the root, has two designated ports. Region123 has one root port, providing its path to the root bridge, and one alternate port, blocking the remaining link to avoid loops. Another term to remember is boundary port, which refers to a port that connects to a link in another region. The wording here is important. This doesn't mean that any port connected to another region is a boundary port. For example, Region 123's 2 ports here are boundary ports, but Region 456's aren't. The reason is that the links between Region 123 and Region 456 are considered part of Region 456, because Region 456 functions as the designated bridge for both links. Therefore, Region 123's 2 ports are boundary ports, because they connect to links that are part of a different region. And Region 456's ports are not boundary ports, because they connect to links that are part of the same region. Now let's take another look inside these 2 regions. Each region runs its own IST, internal spanning tree, which is MST instance 0. Between them, we have the CST, which we just covered. The combination of the CST and the ISTs is called the CIST. The common and internal spanning tree, CIST, is the combination of each region's IST, the connections within each region, and the CST, the connections between regions. The root bridge of the CIST is the switch with the lowest bridge ID, in MSTI 0, among all regions. As a reminder, here is the MSTI 0 priority of each switch again. Switch 5 has the lowest bridge ID because of its priority of 0, and is therefore the CIST root bridge, the root bridge of the entire CIST. And that is why Region 456 is the root from the perspective of the CST. Here is that view of the CST again, connecting Region 123 and Region 456. Region 456 is the root bridge because it contains the CIST root, the single switch with the lowest bridge ID in the LAN. Now, before we connected these 2 regions, we saw the port roles of each region's internal spanning tree. Here are the port roles in Region 456. They are the same as before, with switch 4 and switch 6 selecting their best path to switch 5 as their root port. Switch 6 disables G01 to avoid loops within the IST. However, Region 123's topology is different from before. Let's see why. When the 2 regions weren't connected, switch 1 was the root bridge. However, with the 2 regions connected, switch 2 becomes what's called the CIST regional root. Let's see what that means. The CIST regional root functions as the root bridge of the region's IST, also called the IST root. So switch 2 now functions as the root bridge of Region 123's IST. And how do we determine which switch functions as the regional root? First of all, the CIST root, switch 5 in this case, is the CIST regional root of its own region, Region 456. So switch 5 is both the CIST root of the entire LAN and the CIST regional root of its own region. Let's quickly confirm that by looking at Show Spanning Tree MST 0 on switch 4, which is in Region 456. The root has a MAC address ending in 84F8 and priority 0. And same for the regional root, MAC ending in 84F8 and priority 0. Both of these are switch 5. Switch 5 is the CIST root of this whole LAN, making it the CIST regional root of Region 456, and therefore it functions as the root bridge of Region 456's IST. In other regions that don't contain the CIST root, the switch with the lowest external root path cost through a boundary port becomes the CIST regional root. I'll explain what external root path cost is in a second, but this is why, despite switch 1's lower bridge ID in the Region 123 IST, switch 2 becomes the region's CIST regional root. Switch 1 has no boundary ports, so it is not a candidate to become the CIST regional root. Switch 2 and switch 3 each have 1 boundary port, so they are the 2 candidates. To see why switch 2 was selected over switch 3, let's first examine what external root path cost is. External root path cost is the cost between regions to reach the CIST root. For example, the cost from switch 2 to switch 4, which is 20,000 because these are gigabit Ethernet ports. External root path cost doesn't include the internal root path cost. For example, the cost from switch 4 to switch 5 within Region 456. Let's take a look at the external root path cost of switch 2 and switch 3. So both switches have an external root path cost of 20,000, the standard gigabit Ethernet cost. With both of them tied, What do you think is the tiebreaker that makes switch 2 become the CIST regional route instead of switch 3? It's switch 2's lower bridge ID, 8192 versus switch 3's 32768. So switch 2 becomes the CIST regional route instead of switch 3. And this is why switch 2 G02 is a root port in the CST, whereas switch 3 G02 is an alternate port. The region's root port leading to the CIST route, switch 5, must be on the region's CIST regional route. Let's check it out in the CLI by looking at the output of show spanning tree MST0 on switch 2. The root bridge has a MAC address ending in 84F8 and a priority of 0. It's switch 5, as we know by now. Switch 2's root port is G02, and its path cost is 20,000, as shown in the diagram above. And then it says, regional route this switch. This is switch 2, of course, since I used the command on switch 2. Finally, here are switch 2's interfaces. Notice the part I highlighted, bound RSTP. This means that G02 is a boundary port, and it uses RSTP mechanics to interact with what it views as a single logical neighboring switch, Region456. Remember what I said earlier. Each MST region appears as a single switch to the outside world. So switch 2 and switch 3 see Region456 as one logical unit. And this is why only the external route path cost is taken into account. Switch 2 and switch 3 don't see the internals of Region456. When switch 2 and switch 3 receive BPDUs from the Region456 switches, the advertised cost is 0, and switch 2 and switch 3 use that cost value to make decisions about the topology. Next, let's examine the same output on switch 3, which is not the regional route. It shows the same route information as on switch 2. This is switch 5's info, the CIST route. Let me point out the port and path cost values shown here. G01 is this switch's, switch 3's, root port, leading toward the CIST regional route, switch 2. As the diagram above shows, G01 is indeed switch 3's root port. And path cost 20,000 is this region's external path cost, via switch 2 G02 to the CIST route. So although this output is on switch 3, this path cost is switch 2's external path cost. Okay, next we have output about the regional route. The regional route is switch 2, of course. Internal cost 20,000 is this switch's, switch 3's, internal route path cost to the CIST regional route, so switch 2. So it's the cost within Region123 to reach switch 2. Switch 3 is directly connected by a gigabit Ethernet port, so the cost is 20,000. And finally, here are switch 3's interfaces. Once again, I've highlighted bound RSTP, indicating that switch 3 G02 is a boundary port, just like switch 2 G02. And now, let's take a quick look at the same command on switch 4, which is in the same region as the CIST route, switch 5. Notice the path cost of 0. If the CIST route is in the same MST region, the switch's external route path cost is 0. But it will still have an internal route path cost, as shown here. It's 20,000 in this case, because switch 4 is directly connected to switch 5. Okay, we've covered several new concepts. So before moving on to the final section, let's review what we've covered, comparing the IST, CST, and CIST. The IST, internal spanning tree, is a special MST instance, instance 0, that runs in each MST region. It is the only instance that sends and receives BPDUs. In this diagram, you can see two ISTs, one for Region123 on the left, and one for Region456 on the right. Here are the port roles for Region123's IST, with switch 2 as the root, and here are the port roles for Region456's IST, with switch 5 as the root. The CST, common spanning tree, is the spanning tree of connections between MST regions, and other switches that don't run MSTP, if there are any in the network. In the CST, each MST region effectively functions as a single logical switch. So this CST has two logical switches, Region123 and Region456. Region456 is the root, and here are the port roles of each port. Then we have the CIST, the Common and Internal Spanning Tree, which is a combination of the ISTs from all MST regions and the CST. The CIST route is the route bridge of the CIST as a whole, and that is switch 5 in our example network, because it has the lowest bridge ID. The CIST regional route functions as the route bridge of each region's IST, and provides the region's path to reach the CIST route. That's switch 5 in Region 456, because switch 5 is the route bridge of the CIST as a whole, and switch 2 in Region 123. Remember what a spanning tree is: a subset of the network's topology that leaves exactly one active path between any two switches in the tree. In each IST, each non-route switch has one active path to the CIST regional route. In Region 123, switch 1 and switch 3 each have one active path to reach switch 2 via their route ports. And the same goes for switch 4 and switch 6 in Region 456. They each have one active path to reach switch 5. Then in the CST, each region has one active path to reach each other region. In our example network, Region 123 and Region 456 have one active path between them, the connection between switch 2 and switch 4. Then the ISTs and CST combine to make the CIST. In the CIST, each switch has one active path to reach the CIST route. In our network, every switch except the CIST route, switch 5, has one route port through which it can reach switch 5. So although each IST is a distinct spanning tree, and so is the CST, they combine to form a coherent whole in the CIST. Okay, let's rewind a bit and look back at this slide from earlier. So far, we've spent most of the video focusing on MSTI 0, which is the IST, the CST that connects the ISTs, and the CIST that encompasses all of them. But in most cases, we don't assign active VLANs to MSTI 0. It's only used for sending and receiving BPDUs and building the ISTs, CST, and CIST. What about the MST instances that actually carry regular network traffic? In Region 123, we have VLANs 1 to 100, with 1 to 50 mapped to instance 1, and 51 to 100 mapped to instance 2. And in Region 456, we have VLANs 1 to 50 and 101 to 150, with 1 to 50 mapped to instance 1, and 101 to 150 mapped to instance 2. So let's see how each of these instances works. First, keep in mind that each instance is local to its region. Although they use the same numbers, Region 123's instance 1 is a different spanning tree from Region 456's instance 1. And the same goes for each region's instance 2. Let's look at Region 123's instance 2, which VLANs 51 to 100 are mapped to. Because VLANs 51 to 100 are only active in Region 123, traffic in those VLANs doesn't need to be forwarded between the regions. So basically, you can ignore switches 4, 5, and 6. Here are the port roles of each switch in this instance. Switch 2 is the route bridge of MSTI2 because it has the lowest bridge ID in this instance, with a priority of 4098. And now MSTI2 in Region 456, which is a similar situation. Because VLANs 101 to 150 are only active in this region, traffic in those VLANs doesn't need to be forwarded between the regions. So we can forget about switches 1, 2, and 3. And here are the port roles. Switch 5 is the route bridge because it has the lowest priority of the three. Switch 4 and switch 6 each have one route port leading toward switch 5. Finally, let's examine Region 123's MSTI1 and Region 456's MSTI1 together. Region 123's MSTI1 includes VLANs 1 to 50, and so does Region 456's. Region 123 has its own route bridge for the instance, switch 1, and so does Region 456. Switch 4 is the route bridge in this case. Here are the port roles in Region 123 and the port roles in Region 456. Notice that Region 123 MSTI1 and Region 456 MSTI1 are separate spanning trees, despite having identical instance numbers and VLAN mappings. However, VLANs 1 to 50 are active in both regions, so traffic in those VLANs should be able to pass between the regions. Each VLAN still represents a single broadcast domain, even if that domain is divided into multiple MST regions. Traffic needs to flow between the regions over the common spanning tree that connects them. These are the port roles we covered before for the CST. In Region 456, switch 4G02 and switch 6G02 are designated ports. In Region 123, switch 3G02 is an alternate port, and switch 2G02 is a root port. However, in MSTI 1, we can't use these port roles as is. The root bridge in MSTI 1 is switch 1, and switch 2 already has a root port, G00. Switch 2G02 can't be a root port, so what is its role? It has a new role, the master port role. An MSTP master port provides connectivity between MSTIs in different regions, allowing the VLANs to pass traffic between the regions. The CIST regional routes CIST root port is the master port for all MSTIs. In Region 123's case, switch 2 is the CIST regional route, as we saw earlier, and G02 is its root port for the CIST. It's the boundary port that connects to Region 456. And therefore, switch 2G02 becomes the master port for MSTI 1. Now, above I said that the CIST regional routes root port is the master port for all MSTIs. What about MSTI 2, which we saw earlier? Well, MSTI 2's VLANs, 51 to 100, are isolated to Region 123, so a master port isn't needed. We'll confirm that in a second. But first, let's confirm MSTI 1's master port on switch 2. As I've highlighted, switch 2 G02's role is MSTR, master. This provides the active path between Region 123's MST Instance 1 and Region 456's MST Instance 1, allowing VLANs 1 to 50 to pass traffic between them. And since I mentioned MSTI 2, let's check the same output for that instance. As you can see, G02 isn't even active in Instance 2. That's because the trunk connecting switch 2 and switch 4 only allows VLANs 1 to 50. None of MSTI 2's VLANs are allowed by G02, so it's not active in the instance. Okay, normally before moving on to the quiz, I do a quick recap of what we covered in the video. This time, I'll just show you this chart I made of the various MSTP terms we covered in this video. We covered quite a few new terms, and it's easy to confuse them, so take the time to review these and make sure you understand. I won't read these definitions, so pause the video here and maybe take a screenshot if you want to review. Although there are still plenty of details relating to MSTP that we could cover, the concepts in this video are probably more than you need to know for the ENCOR exam. Now let's move on to do a few quiz questions to test your understanding. Here's quiz question 1. In a LAN with multiple MSTP regions, which switch functions as the IST root bridge of a region that doesn't contain the CIST route? Pause the video now to think about the answer. Okay, the answer is D, the switch with the lowest external route path cost through a boundary port. In a LAN with multiple MST regions, a region's CIST regional route functions as the region's IST route bridge. If the region contains the CIST route, the CIST route is that region's CIST regional route. But the question specifies of a region that doesn't contain the CIST route. In that case, the switch with the lowest external route path cost through a boundary port becomes the CIST regional route, and therefore the IST route. Here's that definition again from the chart with the relevant parts highlighted. Okay, let's move on to quiz question 2. Which term best describes the switch with the lowest MSTI 0 bridge ID in a multi-region MSTP LAN? Pause the video now to think about your answer. Okay, the answer is B, CIST route. The CIST, common and internal spanning tree, includes all switches in the LAN. The switch with the lowest bridge ID in the entire LAN becomes the CIST route, so B is correct. Now, the CIST route also functions as the CIST regional route and the IST route of its region. But those are side effects of it being the CIST route, so B is the best answer. Okay, let's go to quiz question 3. Which port becomes a region's master port for a particular MSTI? Pause the video now to think about the answer. Okay, the answer is C, the CIST regional route's CIST route port. Instead of me explaining it again, let's look at a quote directly from the 802.1q 2022 standard, which contains the current definition of MSTP. A master port provides connectivity from the region to a CIST route that lies outside the region. The bridge port, that is the CIST route port for the CIST regional route, is the master port for all MSTIs. So C is correct. Okay, that's all for the quiz and this video. I hope it was helpful. Thanks for watching. Before finishing this video, let me thank my JCNP level channel members who support me through YouTube channel membership. To become a member, please click the join button under the video. Thanks to Jonathan Makara, Velva Jacob, George, Nasir Chowdhury, Gustavo Macedo, Marcel Lord, Dragos Hernea, Zakib Shah, Mer Salman, Vitaus194, Mark Jackson, Bold 1C1U, Gerald Guillaume, Fristas 1207, Hector Hernandez, Arpad Konivez, 5 Feet, Owad, Daniel Brown, Jose Alvarez, Hussein Yavuz, Samuel Tavares, Kevin Hayes, Roger Bratseth, Brian Grant, Georgi Gemejev, Cats for Life, Adelson Pereira, Farad69, Madmark 50484, Alexandru Stratan, Hiago Bicalho, Lucien Stoichitoyu, DMJ2, Kurt Nell, Dear Diso, Steve Cox, Jasper Yim, Pedro Hartman, Tricky Mickey 123456, Ivano Capuano, Jefferson Steelflex, Toxic, Wilmer Romero, Sinan Sarisinar, Gio, Daniel Andrade, Mike Crumby, Dragos George, Jairo Francisco, Filip Jovanovic, Mateusz Zashinsky, Ruben Hernandez, Electro Jedi, Trevor Goldman, Gavin Paul Tech, Sunny Idigu, Jeffrey C., Chitsinde, Stephen White, Edificare, Fio Hein, Dimitro Lis, Fares Al-Zaharani, Jean-Marcel Belmont, Mikhail Chapsky, Hemanth Jabalpuri, Dariush D., Juan Morales, Gonzalo Nicolas, Doomed Soul, Christine Schubert, Julio Maya, Josie, Egreso, Komlan Kapedemi, Gokhan Doimez, Hashim Rodef, Anand Abyankar, JFlow99, Clyde Mkorobindo, Adekola Ismail Salami, Orlando Flores, Ray Enriquez, Adrian Martinez, MD Danielwitz, Gabriel Afolabi, and GG7. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.